Good afternoon, college algebra students from Roswell, New Mexico. Last lesson that we did was we dealt with polynomials, and I showed you guys how to graph polynomials. Today we're more interested in finding all the factors and all the zeros of a polynomial. So let's start with this simple example, folks. Right here, this is an example of a second degree polynomial. Most of you guys just think of this as a quadratic equation, quadratic expression. But it's also a second degree polynomial. Now, if we wanted to find the zeros of this second degree polynomial, you can see fairly quickly that this factors into x, plus 7 times x minus 6 equals 0, right? Again, this is an easy one. It's one that we've seen before, this idea of finding the right combinations of numbers. 7 minus 6 gives you the one that's really in front of that, right? So this factorization is useful because we see that x equals to negative 7 or 6 are the solutions to this polynomial. They're the zeros. So in other words, we call these values zeros, folks. It's kind of confusing, but they're non-zero values that makes the entire polynomial equal to 0. That is, P at negative 7 is equal to 0, and also P at 6 is equal to 0. And you see each of these correspond to factors. This corresponds to the factor x plus 7, all right? And this corresponds to the factor x minus 6. So they actually glorify this with a name. Any zero corresponds to a factor, and that's obvious. Maybe you haven't talked about it or thought about it this way, but anytime you have a zero, you have a factor. Another way of putting this is that R, we'll use the letter R, okay? R is a zero of the polynomial P of x. Oh, I'm still on the screen for you. There we go. And y'all, I use this double arrow just to indicate what we call logical equivalency. Folks, okay. If and only if, this means if and only if they're just equivalent, x minus r is a factor. Is a factor. Now, again, we've already talked about this. We just haven't talked about it this way, really. So make sure this makes some sense to you. R is a zero of this polynomial if and only if x minus r is a factor. And that's exactly what this says concretely. You see, negative 7 is a zero if and only if x plus 7 is a factor. Right? And this is just saying it more in general. Right here we're using the concrete values negative 7 and 6 and showing the corresponding factors. Here we're saying R is a zero of this polynomial if and only if x minus r is a factor. Now I hope this isn't, sometimes math notation makes things harder than it really is. This is something that's obvious, but we're just making it formal, okay? Now this is the so-called factor theorem, okay? They actually give this a name. They call it the factor theorem. It's a little overkill in my opinion, but we call that the factor theorem. All right. Now we're going to use that truth to answer this question right here. See, now this one isn't so obvious whether it factors or not. This is a third degree polynomial, folks, right? Over here it was real obvious that this factored. Very, very obvious, the factorization, right? Over here we go, what in the world? We got 4 terms here. Is it really going to factor? Well, this theorem, the power of this theorem right here is really going to come into play right now. All we have to do is evaluate the polynomial at 5. Okay. We can just substitute 5 into the polynomial. And if we do that, folks, we get 125 minus, folks, if you put 5 right there, you get 25. This is 75. Okay. Now, if you put 5 right there, you get 25. And then plus 12, right? Right, ladies and gentlemen, you see what we're doing here? Rather than having to figure out how to factor this in some more involved way, all we have to do is take this 5 and put it right in there, okay? And if this is not equal to 0, and it isn't, and y'all, you can look at this fairly quickly, and you don't have to tell me, it's just not equal to 0, right? You can see that by looking at it. This is 50, and that would be 75, so it would be equal to 87, right? But the important point is it's not equal to 0. So the only way this could be a factor if this was equal to 0. So the answer is no. Okay, no. All right. So that's the answer to that question. As far as that question goes, you're done with it. All right, you're done with it. You just used the factor theorem and this nice little truth that was discovered on the easier problem. Okay, that's the answer to the question. Now, I would like to show you another approach on this, folks, and it's called long division. Another way of doing this to actually see a little bit more about the nature of the problem is to perform what they call a long division. All right, and so the way that's done, and this might have been the way that you guys would have tried it if you knew how to do long division. So let's write this down. Okay, so we'll just recopy this problem right here, x cubed minus 3x squared. And some of you may have seen this. It's kind of a tedious process, but it's just based on how you do division with regular numbers. It's just you're having to deal with polynomials here. Okay, you write it like this, folks. This is called, I believe, the dividend. This is called the divisor. And we're going to try to actually divide this expression right here into this expression. Now, the way you start is just you write an x squared here. And if you look at how you divide numbers, this is really the same thing, except you're just working at exponents. Where did I get this x squared? Well, see, x squared times x gives you this x cubed right here. Yeah, I'm hoping I'm not going to run out of room here. Now, this times this gives you minus 5x squared. Now, you can think of 0 terms here if you want to. Some people like to write this in like this, plus 0, so you know that you're subtracting. Now, if you just think about what you're doing with numbers, it's actually the same thing right here. If you're dividing two numbers together, you're doing a process sort of like this. But so what I do, I like to put a little circle minus sign out here to let you know that you're subtracting. Okay, so those go away as desired. Now, this would give you 2x squared. But you see, you're minusing this in a columnar fashion. So this minus sign here turns that minus sign to a plus sign. Now, some people just change the signs on this. It's totally your business how you handle this, okay? But this is how I've shown it for a while. Now, 5x minus 0x is plus 5x. And then right here you get 12. Now, you don't know that you're done until this degree is bigger than this degree right here. So what you would do next is write down plus 2x. Sorry, y'all, why did I do that? 2x times x gives you the 2x squared you see there, right? 2x times x gives you the 2x squared you see right there. And I hate to keep saying this, but if you just look at what you're doing with numbers, you're kind of doing the same thing, except you're not having to deal with exponents and letters. Okay. Now, this times this is minus 10x. Okay. And then, so we're good. So let's see what we got there, a 2x squared. Now, you can put a plus 0 there if you want. Plus 0. All right. Now, when you subtract here, folks, when you subtract right here, you end up, this goes away, you end up with 15x plus 12. Again, folks, 5 minus a negative 10 is the 15x you see right there. Okay? Now, we still have a power of x that we can get rid of by putting a 15 right there. Okay? By putting a 15 right there. And so, let's write down 15x. All right, folks, now, minus 5 times 15 is minus 75. And when you put the minus in front of the whole thing, this ends up being 87 as your remainder. Okay, 87 is your remainder. Now, folks, if you take a look right here, these numbers right here added up to 87. Okay, 125 minus 75 is 15, plus 25 is 75, plus 12 is 87. So you see, this is a shorter way of determining whether something's a factor. A much shorter way of determining whether something's a factor. The fact that you have a remainder means that x minus 5 could not have been a factor to begin with. Now, what I'm going to do right underneath this, folks, I'm a little out of room, but I've thought about this in advance for once. What this really means, another way of looking at this, and let me see if I can slide up here just a little bit and give us some more space. Okay. Now, what all this really means is that this quotient, we call this object right here the quotient. This is called the quotient. That's Q-U-O-T-I-E-N-T. Okay, quotient. All right. And this right here is called the remainder. I'll just call it REM, folks, remainder. REM abbreviated remainder. All right, now, another way of thinking of this to make it, give you a little more context to this is that all it means is that the original polynomial we were dealing with okay. And now what I'm going to do is recopy this quotient. And then plus the remainder. And if you just think about how when you divide with numbers, it's the very same thing. Like if you said, what is 16 divided by 5? Okay, well, it's equal to 3 with 1 left over, right? Well, it's the very same thing right here. This is that 1 would be your remainder. And and just let me write this right underneath here, just so, say if I did 16 divided by 5, right? Okay. That's equal to 3 and plus 1/5, right? Well, that's really, if you multiply through by 5 right here. Is that visible, folks? This lighting here is horrible. Let's see. There we go, a little bit better. Okay. Now, y'all, you can rewrite this, of course, as 16 is equal to 5 times 3 plus 1, right? See, that's the exact same structure as you see right here. You see this part right here? It really lines up with this. It's just that we're dealing with polynomials. You see, this 1 is the remainder here. This 87 is the remainder here. The 5 and the 3 correspond to this and this. And then the 16 is just like the whole original. So, I mean, the structure of what we're doing with polynomials really lines up with just very, very simple arithmetic. It's just you're having to deal with variables that have exponents that makes it seem like it's completely different. But it's really essentially the same thing as far as structure goes. Now, there is one other approach on this that you may prefer that's easier than going through this horrible long division. You can actually this is called synthetic division. Okay, and let me just show you the process on that. Okay, what you do is take your original problem. 1's understood to be in front of anything, right? Okay. And then you put the minus 3 here, 5 and the 12. All right. And then what the process here is to bring this 1 down. All right. And then what you do is you do 5 times 1 is 5. And you add right here, not subtract, and you get 2. 5 times 2 is 10. All right. Add here and you get 15. See, and 5 times 15 is 75. Add and you get 87. Isn't that a cruel truth? All right. So that's this, y'all. This is called synthetic. This is called synthetic division. But see how it lines up exactly with what happened. And I barely left enough room there, didn't I, folks? See all these numbers, 87, 87. And you see there's a 1, 2, 15 right there. 1. Okay. So 1, and it all lines up nicely. 1, 2, and 15 and 87. 1, 2, 15, and 87 right there, right? Okay. And again, y'all, this is called synthetic division. It's an easier way to handle things as long as you're dealing with what they call linear divisors. Like this is called a linear term. Synthetic division doesn't work like if this were x squared, but it works for these kind of problems which come up quite a bit, actually. So this is called synthetic division, right? Now, okay, that's going to lead us into the very next problem, folks. This whole build-up here is going to lead us into the very next problem. Now, what I want you to do is just work. You don't have to work. I just want you to answer this question. So this is homework problem number 1. So you can use synthetic division. You can use long division. You don't have to go through everything I just went through, but this is homework problem number 1, okay? Homework problem number 1. And just an answer to the question, okay? I showed you a lot more as a build-up to what we're going to do on the next problem. But all you have to do is you can either use synthetic division or long division to answer this question. Okay, that is it. That is it for that problem. You do not have to go through everything I just showed you. Okay, now let's move along. All right, y'all. Now this looks totally radically different than what we just did, but it's actually just one more additional fact. Okay, it's just one more additional fact. Now, this really looks confusing if you read this. This is called the rational zeros theorem. And it gives us a way to find any fractional zeros. Any rational and fraction mean the same thing, right, folks? Fraction. A rational number is a fractional number, right? Sorry. Fractional numbers. Okay, so I just never will master this, folks. I want enough room so you can see it, but then I run out of room. But now, again, this looks like a mess here, but it turns out to be quite easy to work with. Okay? Now, all you got to do is remember that the only thing that really counts is this number and this number. Okay? Y'all, this is called the constant term. This is called the leading coefficient. This is called the leading coefficient. If you take a look here, it says any fractional zero has to be P over Q, where P is a divisor or a factor of the constant term. Okay, and Q is a factor or divisor of the leading coefficient. So this would be your A sub n, right? This would be your A sub n as far as the problem, as far as this theorem goes. You don't really have to think of that every time, but that's your A sub n, and that's your A sub 0 as far as the notation they're using here. A sub n, and then you end at A sub 0, right? That's how all these formulas have to be. You can't have numbers in them because they need to work for any case, so they can't have any numbers, but you get the idea of what all these coefficients actually mean. Now, so it says find all the zeros for the following polynomial. Now, so a way to start is to at least have some sort of springboard in how to do the problem is list all the P's or Q's. So you see again, the P's are going to be divisors of this number, and the Q's will be divisors of this number. So let's just start writing some of these down. Okay, 5 and 1 are the only divisors of 5. So you can write down 5 over 8, all right, which is a divisor of 8. You can write down 5 over 4. Okay, which is also a divisor of 8. 5 over 2. And 5 over 1. Right, folks? And you see, we're doing this PQ business as we speak, but we've just done it for 5. All right? See, these are the Q's down here, but the Q's are all the divisors or factors of 8, right? 8, 4, 2, and 1 are the only numbers that divide evenly into 8, right? Okay. Now, but 5 is not the only number. Your next row will be 1 over 8, 1 over 4, 1 over 2, all right, and 1 over 1. All of these could be plus or minus. The negative numbers are also divisors. Like, 5 is equal to minus 5 times minus 1, right? 8 is equal to minus 4 times minus 2. So all of this could be plus or minus, right? I'm not going to write it in front of each one of them, but all the plus values and all the minus values are potential rational zeros. Now, okay, wonderful. So this is our P over Q list right here, right, folks? This is our P over Q list, if you will, of potential rational zeros generated by this theorem. Okay, it's really not so bad. It's just kind of it's tedious, but now. So why did I give you this graph? If I hadn't given you this graph, you would have to try each one of these to see if it was equal to 0, right? But what I would like you to do, and I'll just pause just like I would if I was face-to-face with you guys. Can you see a number here, a crossing, that might correspond to one of these numbers in this list? Okay. Now this number over here is just a little bit to the right of -2, so it might be, it could, I don't see any number in this list. This is a number between 1.5 and 2, right? Well, I don't see a number in this list that's anything like that, right? This is a number right here. This 0 is between -2 and -3/2, right? This would be -1. That's -3/2. So I don't see any number in this list that's between -3/2 and -2, right? Do you? Not a single one. Now let's go over here. Maybe right here, this might be 1/2, but it looks a little too far to the right to be equal to 1/2, right? A little too far to center. Okay, but now right here, you start thinking there's some chances, right? Okay, this would be 3/2, right? This is 3/2. So what's halfway between 1 and 3/2? Well, it's actually 5 over 4. Remember, think of right here, 3/2 is the same thing as 6 over 4, right? Okay, so it's very easy to believe that 5/4, that this value is 5/4. Okay, so let's see what happens using what we learned in the previous section, or the previous demonstration on synthetic division. What I'm going to do, folks, is I'm going to make the assumption that is equal to 5 over 4. All right. Now, the potential rational zeros is all of this stuff right here. Okay, this is the potential rational zero. So I just did, that's this part of it right here. Now we're actually going to try to find all the real zeros. So what I'm going to do, folks, is do the 5 over 4 that we obtained from the graph. Okay. Yeah, let me. This is always. Hopefully that's visible to y'all. Okay. So y'all, I'm going to do the 5 over 4. And then I'm going to apply the synthetic division here. It's a lot easier than doing the long division. I don't think anybody can test that view. So I'm going to take this 8, take this 2, take this -19, and take the 5. Okay, y'all, this is the synthetic division. Now, we're expecting to get 0 out of this, right? Because according to the graph, 5 over 4 is the number in the list that looks most promising right now, right? Again, if we didn't have this graph to go off of, you'd just be checking each one of these by hand. Very tedious, not too fun. Not a whole lot of fun on an Easter Sunday, right? Especially when you can't go to church and do your Easter egg hunt, right? Now, y'all, so what I'm going to do, just like before, bring the 8 down, okay? Bring the 8 down. Now, this, no calculators, folks. I do want you coming out of the course knowing how to work with fractions. 8 times this number, 8 over 4 is 2. 2 times 5 is 10. So you place a 10 right there. Okay, you place a 10 right there. I'm going to try something here. Can y'all see? Is there enough? Good. Okay, there's enough light just coming in from the window here. That's better. Y'all, sorry about that. All right. So, y'all, what did I do right here? I brought the 5/4 here. Now, 8 times this number without a calculator, 8 over 4 is 2. 2 times 5 is 10, right? You add right here and you get 12. Okay. Now, in a similar fashion, you take this 12 and multiply it by the 5 over 4. Okay, don't do 5 times 12 equals 60, please. 12 over 4 is 3. 3 times 5 is 15, right? So you're going to put the 15 right here. Now, what happens right here, folks, when you add? When you add, you get negative 4. Right? You get negative 4. Again, y'all just have to verify that, but please learn how to do this without the calculator. I do have my ways of testing you on that. Okay? Now right here, if you take this negative 4 and multiply it right there, the negative 4 and the 4 cancel to give you a negative 5, right? Now, again, it's well worth your time to understand how to do the fractional stuff without the calculator. Okay? A lot of y'all are very good at it already, but some of you in the class need to work on that. It's a good skill to have. Just know how to manipulate fractions without having to depend on the calculator. Yeah, good news, right? This is good news. Okay. Worthy of an exclamation mark, right? Good news. Because we did, from the graph, it looked like it did cross the x-axis. And another name for the x-axis is y equals 0, right? So there's your 0. In other words, y equals 0 is another name for the x-axis, right? So we got our 0 here. Now, what does this mean, folks? What does this mean? It means that we now have a way of finding the other 2 zeros. Now, let me, let's see, can I try to squeeze back down? Is that okay with you? Is that? I think that's. I heard a sound. I think that's it. So, now, what can we do right here? We can actually use this information in a very favorable way. We now know that the original polynomial. I'm going to write a little smaller here. That looks like you can see it okay. Is equal to this. X minus 5 over 4. And based on what we did on the last exercise, okay. Now I'll just kind of put the plus 0 there for emphasis. We needed that to be the case because that also, we don't really, you can leave that out if you want. It's just to let you know that 0 actually means something vital here. I'll erase it now just in the name of avoiding confusion. That also means that this is a factor. Now, y'all, while I'm talking here, we already know that 5 over 4 is a 0. So remember, that's what the original problem asked for. It says find all real zeros, right? So we found 5 over 4 is 1 already. Now we can find the other one by setting this one equal to 0. This is a quadratic factor. Let me come over here, and I believe this is going to work out. Good. All right. Good old natural sunlight, folks. I was overkilling. So I had the light on this, and then the sunlight just beaming right through. So that's what was creating kind of that glare situation we had a moment ago. But so we have 8x squared plus 12x minus 4 equals 0. All right. Now this is just back to what we learned way early in the semester. Now, dividing, you could just turn this into a quadratic equation and try to solve it. But notice that 4 is common to all the terms. So if you divide by 4, you're going to get 2x squared plus what do we got here? 4x minus 1 equals 0. Okay. So y'all, again, we already have one of the solutions, but after we solve this, we'll have the other solutions. Now, if you remember working with the discriminant, you can see that this doesn't factor. It doesn't quite factor. There's a remember b squared minus 4ac, you'd get a discriminant of 8 right here. 4 squared minus 4 times this, you would get a discriminant of maybe 24 or something like that. But anyway, this doesn't factor, so you have to use the quadratic formula or complete the square or something. Quadratic's probably the easiest right here. So we'll off to the side here, folks. I'll go x is equal to, and I'm just reciting the quadratic formula, negative 4 plus or minus. Okay, y'all, that's 16 minus 4ac. That was going to be plus 8, right? Because There's a minus in the quadratic formula, but there's a minus right there too for your C, right? Okay, all over 2a, which is, this is your a, right? So 2 times 2 is 4. Okay. All right, ladies and gentlemen? Now, right here you get x is equal to -4 plus or minus the square root of 24. Square root of 24 all over 4. Okay, y'all, now remember it's sometimes useful to simplify this radical. So this would be, you could write this as 4 times 6, right? So this, and that would make this 2 root 6. So you're going to end up with, let me just write the answer. This minus 4 of this minus 4 is going to give you -1. So this would be x is equal to -1 plus or minus, now, y'all, this would, 24, okay, 24 is equal to 6 times 4, so that would be 2 root 6. So this would be root 6 over 2 is your other 2 zeros. Okay, root 6 over 2 is your other 2 zeros. Now, where would they be located? Well, you could probably check on your calculator, but we could just take a look at it like this. This would be, one of the zeros would be -1 minus root 6 over 2. And the other one would be -1 plus root 6 over 2. Okay. Now, if you substitute this number to your calculator, you would get a number that's between -1.5 and -2. If you substitute this number into your calculator, you would get this number right here, just barely a positive number. Okay. So again, I won't just, that's fine. But so this, the way you would write your answer would be -1 minus root 6 over 2, and then -1 plus root 6. We're still on the screen. I love it. Okay, good. Over 2. All right, y'all, we're done. Y'all, tedious problems, but it's just step-by-step work. Don't try to skip any steps, and stick to the routine. Again, I'm lucky I didn't make any mistakes in anywhere. It's quite easy to make mistakes in these sort of calculations. But what I want you to do as your second homework problem, let's see, what do we got here? Let's see, what do we got? Yeah, here we go. All right, y'all. Now, y'all, these are all on the handouts on Canvas. I've already put them there. I have copies for you. Let this be homework problem number 2. Okay. Homework problem number 2. All right. Okay. All right, y'all. This has been longer than usual, but it's kind of 2 lessons bundled up into one. And y'all have a wonder. I hope everybody's going. I know it's so hard. It's so hard right now trying to be motivated and stay on top of things and keep up. But just do your best. You will only be responsible for the stuff that's on the videos that I've been producing for y'all. Okay. You all have a good one. Take care.